Good afternoon, everyone. So today I'm going to talk about reconstructing attack provenance in serverless clouds. This is a joint work from the University of Illinois at Urbana-Champaign and NC State. So if we look at serverless programming model, it's quite different from the traditional web applications. So here applications consist of several small functions that only execute for few seconds or like few cycles. Each serverless application, the logic is constructed as a bunch of workflows, and each workflow consists of several functions, then data stores and other cloud components, and they communicate to each other to get the things done. So this cloud computing programming model makes the functions isolated and stateless, and it has become quite popular in the industry. The reason being that the serverless cloud platforms take away the task of management from the developers. So everything in the backend and the software stack is managed, and you also don't need to worry about auto scaling and load balancing. Based on the request load, you can increase the number of your instances that service the incoming requests, and you can also scale it down to 0 when it's not that busy. Also, the users only pay for the cycles the function executes for, thus bringing down the cost significantly. So do serverless also buy us additional security? So let's look at this example, which is modeled after a proof of concept example of a retail serverless application from Nordstrom. So here is the retail website portal where customers can browse and they can click to launch a function which is a product purchase function that can invoke authorize credit card function, which authorizes the purchase, and then the purchase status can be communicated to the customer through this publish status function. So all these functions are protected by role-based access control policies, and when the request load increases, in addition to scaling up the function instances, the platform also caches them in memory and recycles them to avoid the costly operation of respawning the containers again and again. So we would think that this scenario is more secure because each of these functions, they are just live for few milliseconds, and it's hard for an attacker to get a foothold to launch a time-consuming attack. However, in April 2022, we see a report from Palo Alto Networks threat researchers that in spite of having identity and access management policies in place, 99% of these cloud entities are overprivileged, and 65% of known cloud security attacks are due to misconfigurations. So let us see what will happen if we have a misconfiguration in this credit card database. Let's say an attacker got their hand to some stolen credentials, and they were able to exploit a bug present in the authcc function. Using that bug, they connect to an attacker-controlled domain and they download some malwares, and thus they can steal some data from the credit card database. Now, if they want to get the SQL dump of the entire database, that can be time-consuming, but recall that in the serverless platforms, they recycle the same container again and again, thus giving them enough time to exfiltrate the data. They can also use the downstream functions like publish status, which has access to outbound APIs like phone, message, email, or other APIs that are legitimate to use, and they can launder the data this way. So after we have seen such attack vectors in serverless, the question we may ask is that, do existing systems prevent or at least help investigation of such attacks? We found out that not only these attacks are hard to prevent, there are also like limited auditing solutions that can help investigation of such attacks. Traditional approaches like Linux audit, they do not know about the serverless semantics. So they do not have idea about platform APIs or different function containers or things like container reuse. And there are also these existing provenance-based tools which remove many terminated system events aggressively, which is not useful in this case, because in serverless there are many terminated function executions that are ephemeral. So we have some observability tools as well. These third-party observability tools, they have some features like distributed tracing and cost analysis, but they have strict usage limits, and mostly they are runtime and platform dependent. So here we see an screenshot from a tool called Epsagon, which is a cloud security tool. So here we can see that this tool keeps track of the inter-function communications at a coarse grained level, and they also track some function execution information like the execution time, but these informations are not as helpful in investigating the attacks we just discussed. So in this talk, I am presenting Alastor, a complete auditing solution for serverless clouds that use data provenance techniques. The first question that informed the design of Alastor is that what are the different types of entities and activities that we need to audit to preserve helpful forensics information for serverless attack investigation. So in the serverless function instances, we have this request handler that services the request that comes in from the application gateway. When a request comes in, the function executor creates a process P that achieves the task of this function. We design a lightweight Alastor provenance collector module that is local to this function instance. It achieves a list of tasks, the first one being tracing the system call that is being invoked by process P. It also keeps track of all inbound and outbound connections in this instance. We also look at the port bindings to keep track of which process is creating which network connection. All of this information and logging information from the request handler is summarized in a form of local provenance graph that preserves all the causal information between these different events that are happening in this instance. So now that we have these local provenance graphs at these different function instances, the next question we asked is that how we can meaningfully combine all this information to facilitate attack investigation. For that, we take help of the serverless platform services and the logs preserved by them. We get the information about what IP addresses are assigned to which instances and also which requests are serviced by which instances. Based on this information, we stitch the different local provenance graphs into a global provenance graph that explains the behavior of the entire application. Let us get back to the serverless attack example, where a bug in the authcc function was exploited to steal some data from the credit card database, and then through repeated invocation of this function, the attacker got enough time and then exfiltrated the data through the public status function using legitimate platform APIs. So we implemented the attack within the Hello Retail application, and then we traced the attack behavior using the Epsagon tool. This is the graph we get from Epsagon. They keep track of the inter-function communications and also the request latencies. But we do not see enough information to investigate the attack. We get a tiny bit of evidence in the abnormal execution time for the attack trace, but we do not know why this is happening or how this is happening. This is how the provenance graph looks like when we trace the attack with Alastor. From the local graphs, we get the information about the network communications that are being created from the instance itself or being received at the instance, and also different system events inside the function instance are recorded. Then at the global level, we have information on every container that was spawned and every request they served. We also track the inter-function communications among the different cloud components in this setting. If we take a closer look at one of the containers, we see that request 1 is coming into the auth.cc function. Then it's exploiting the bug already present in the function and creating a connection to an attacker-controlled server to download some malicious files. Then if a request comes in quick succession, then they already have this malicious files handy, and they can use that to steal some data from the credit card database. So this is how the container reuse attack looks like when we trace this attack using Alastor. In our paper, we have more examples of such serverless attacks, so please do give our paper a read. To conclude, Alastor can be used to diagnose the serverless-specific attack techniques like container reuse and exfiltration through downstream functions. It also imposes manageable performance overhead, but in exchange, we get a lot improved forensics capability. And Alastor logs can also be used with other tools like DeepLog for intrusion detection. Thanks for listening to my talk, and I'm happy to answer questions.